Okay, let's get started. So today we're going to be covering a fun topic because a lot of what we'll be covering is stuff that's extremely recent. Now, topic-wise, really the question that we're going to be focusing on for the lecture today is how should we be defining tasks for good meta-learning performance? We've talked a lot about different meta-learning algorithms, and we've talked about one way to construct tasks. We've also looked at some case studies. But in this lecture, we're going to talk about some of the different failure modes that can come up, or some of the situations where maybe it's pretty hard to construct tasks, and some of the things that you might be able to do in those situations. So in particular, the plan for today is to very briefly recap the three different meta-learning approaches that we've talked about, as well as the kind of ways to construct tasks that we've talked about. Then we're going to talk about memorization in meta-learning, and when it arises, a potential solution to that. And then lastly, we'll talk about meta-learning when you don't have any tasks that are provided and ways in which the algorithm might be able to automatically come up with tasks that it should solve in a way that can allow it to still be able to quickly adapt to human-defined downstream tasks. As I mentioned, these topics are really new. They're really at the bleeding edge of research. And so just as a disclaimer or a warning, potentially a lot of the things that we're going to be covering today are really at the cusp of what we know and what we've experimented with. And so I encourage you to ask questions, but for some of those questions, I may not know the answer. They may be still open problems and open questions in the field. With that said, the goals by the end of the lecture is to help you understand how when memorization in meta-learning may occur and understanding techniques for constructing tasks automatically. Okay, so let's get started. So first, let's recap the different approaches that we talked about. So I think a couple weeks ago at this point, we talked about Blackbox MetaLearning, where you have some neural network F that takes as input a data, also takes as input a new data point, and makes a prediction for that new data point. So the key idea is to kind of parameterize a learner as a neural network. This approach is very expressive, but it's also a very challenging optimization problem. We also talked about optimization-based meta-learning algorithms, which instead of using a neural network to parameterize the learner, that use an optimization process, and any free parameters of that optimization process, like the initial parameters or like the inner learning rate, can be meta-learned. So the key idea is to kind of essentially embed this optimization inside the learning process and optimize end-to-end with respect to those parameters. And this is what you'll be implementing as part of homework 2 that came out today. The benefit of this is that you have the structure of optimization embedded into the meta-learning process. The downside is that it typically requires a second-order optimization, which can be a bit more heavy or computationally intensive. The good news, though, is that various deep learning libraries that we have can typically handle the more arduous parts of the second-order optimization for you. And then lastly, last week we also talked about a third class of meta-learning algorithms, which I referred to as nonparametric MetaLearning algorithms. And the way that these meta-learning algorithms approach the problem is they first embed the test example and all of your training examples. And then they do some sort of nearest neighbor by comparing your test embedding to all of the training embeddings, find the one that's the most similar, such as this one right here, and use that to predict the corresponding label. So really the key idea here is to use a non-parametric learner, which is basically everything shown in green here, with a parametric embedding or distance function, which are each of the arrows shown in blue. For example, the non-parametric learner may be something like k nearest neighbors, 2 examples, or prototypes. And then the parametric embedding is what the meta-learner is learning in order to make this non-parametric learner successful with only a few examples. The benefits of this is that it's easy to optimize and it's computationally very fast. This is entirely a feed-forward process. The downside is that it, so far at least, has been largely restricted to classification problems. Okay, so that's kind of a brief recap of the 3 meta-learning approaches that we've talked about. And then we've also talked about different ways to construct tasks. So one of the canonical ways to construct tasks is to use labeled images from previous classes in order to allow you to solve n-way classification problems with this small number of examples. But we also looked at case studies that allow you to adapt to regional differences using labeled data from other regions, and also things like few-shot imitation learning, where you use demonstrations for previous tasks. The essence here, though, is that you construct tasks using labeled data from tasks that are representative of the kinds of tasks that you'll be seeing at test time. Okay, so that's a brief recap. Now let's talk a bit about some challenges that come up when we construct tasks for MetaLearning. So in the example of few-shot image classification, the tasks that we've looked at look something like this, where we constructed a training set and some test examples. And we constructed this train set and test set for basically each of the tasks in our training set. Now, one of the things that we did when we constructed these tasks is we randomly assigned labels to each class. So for example, in this first task, the class of mushroom may get a label of 1, whereas in this third task, the label of mushroom might get a label, the class of a mushroom may get a label of 0. And so we're randomly assigning different class labels to image classes for each task. And this means that the tasks are what I will call mutually exclusive. And what I mean by that is that there isn't just a single function that can solve all of these tasks. And that's because we're assigning different labels to different classes. So we don't have a single function that will both assign a 0 to a mushroom and a 1 to a mushroom. And likewise for classes like pianos that also have different labels for different tasks. Okay, so one byproduct of this way that we're constructing tasks is that the algorithms must use the training data in order to figure out what the label ordering should be. So it actually has to look at this training data, look at kind of what ID was assigned to mushroom, what ID was assigned to piano, and so forth in order to make accurate predictions on the test examples. Okay, so now with this in mind, this is kind of the canonical way that we construct tasks. What happens if the label order is consistent? So in particular, say that we constructed tasks like this, where we always assigned the label 1 to mushroom, the label 2 to this kind of dog, the label 4 to carousel, the label 1 to landscape, and so forth. So based on this, I guess I want to run a little poll to see what people think. And in particular, the question will be, what happens when the label order is consistent? So if we meta-train a model on the tasks like this with a consistent label ordering, and then test them on new tasks with held out classes, what do you think will happen? So I'll launch a poll, and I'll also give you a minute to think about it. And the different options are, will it do much better than the shuffled label ordering, slightly better than the shuffled label ordering, the same as before, slightly worse, or much worse? So we have some votes coming in. Mentioned in the chat that he accidentally did this in homework 1. So I'll wait a little bit longer for a few more votes to trickle in. Okay, so we'll end the poll there, and I'll share the results. So most of you think that it will do much worse, although it's a bit, it's not, different people think different things. So I'm curious why people put the answer that they put. So did anyone say that they think it performed, I guess, does anyone want to share kind of their reasoning for why why they think the answer that they put? You can raise your hand.
So I put much worse, and the idea there was that if there is an ordering of classes, and if you use the model like an LSTM, then we could see maybe unit learning features that are specific to a certain class, and then when you shuffle the ordering at test time, then they'll do worse.
Yeah, so the idea there is that the tasks that will be given at test time will have new classes, and so you won't necessarily know the ordering. And so if we learn kind of things that are specific to these training classes with this label ordering, maybe it won't generalize to that kind of new test task. Any other opinions or thoughts that people want to share?
Does this make it easier or more possible to shuffle? So for example, if we shuffle, at least we still have all dogs be 2, all, I guess a dog is not 2 in the second, in T2, but at least maybe all birds, actually, but basically it enables us to shuffle. So I thought maybe we'll do better.
I guess it's not clear exactly what you mean by it enables us to shuffle. So if you're training with these classes that have a consistent label ordering during training, why do you think that makes it easier to shuffle? Just trying to understand your reasoning.
No, in fact, maybe I didn't understand the idea of working with consistent label ordering. From what I thought all carousels are 4, all dogs are 2, and something like that. And so if you see a dog, the model is able to predict it too. But it looks more that it's more to do with the order of images than what's in the images. Maybe I didn't fully understand the question.
Okay. And do you want to share your thoughts?
Yeah, so I put much worse, and that's because the model will learn what class belongs. So, for example, in this case, it will learn that a dog is always class 2. So during the training, it will always classify it correctly. But for held out classes, it won't be able to generalize. It will be more like a supervised, I guess. Yeah, it will be more like supervised use case rather than meta learning.
Yeah, so kind of just to summarize, it may just learn to kind of do a supervised regression to the labels rather than actually learning to adapt to the data set, which won't, if it's more like supervised learning, then it may not be able to quickly adapt to new examples. And then I see some more hand raised. You want to share your thoughts?
Yeah. I just wanted to ask a clarifying question. So we've mentioned the order a couple of times, but in this case, the algorithm doesn't necessarily learn the order, right? It's more about not being able to learn how to learn instead of learning the supervised learning task. Is that like a good summary?
Yeah, so I guess what I meant by ordering is basically that the assignment of class IDs to classes is consistent.
Right.
Yeah, so maybe ordering isn't quite the right way to describe that.
Yeah, okay. No, then it makes sense. Thanks.
Okay. Cool, and there are a couple more hands raised. Do you want to share something?
Yeah, sure. I put much worse. I think it might be problem dependent on whether it's slightly worse or much worse, but my thinking was that if the ordering is consistent, then at meta test time, the model can just, or during meta training, if the labels are consistent, then the model will learn to ignore the label in detrain. It no longer needs the Y in detrain because it can memorize all of the classes in the meta training set.
Yeah, exactly. So in some ways, the outline of the lecture sort of maybe gave it away what the answer was in some regard. But when you have this consistent assignment of labels to classes, then the tasks become non-mutually exclusive, such that a single function can solve all of the tasks. And this means that your meta-learned model can simply learn to classify the inputs irrespective of the training data that's passed in. So it can basically like completely ignore the training data sets, just learn to classify everything in the test sets per task. And then when you give it a new training data set, it won't be able to actually process that because it didn't learn to process the training sets during meta training. And so in particular, what can happen is if you have a black box model, it can simply just ignore all of the training inputs here and simply just classify the last input that's provided to the model. And likewise with an optimization-based model, it can also just ignore the data set and learn a set of initial parameters that sort of then somehow renders the optimization in the inner loop kind of irrelevant. For example, if it can already predict all of the examples correctly, just by looking at the image and not by looking at the labels, then the inner gradient will be 0, and that won't have any impact on the network, and that will effectively lead it to ignore the training set also. So in particular, now if you meta-train a model with this label assignment that's consistent and then evaluate it to a new task with held out classes, with classes like this, for example, it doesn't know what the label should be for each of these classes. It doesn't know what the assignment should be, if it should be 0, 1, 2, 3, or 4 for each of these classes. And because it learned to ignore each of these training data sets, it's also going to ignore this training data set of the test task, and it won't be able to effectively make predictions on the test examples. And if you actually run MAML on these tasks, you'll get performance that looks like this. So in this case, this is a non-mutually exclusive version of Omniglot, where you apply the same label ID to each class consistently across all the tasks. And you see performance drops from performance roughly in the 90s to accuracy numbers that are around 7.8% and 50.7% in these different cases. So you see a pretty substantial drop in performance when you make the label assignment consistent. Now this seems like it shouldn't, like, if you think about how you construct tasks, it seems like this, like, ideally it shouldn't make this huge of a difference depending on like how you assign the labels. So maybe let's kind of dig into this problem. It's asking, does this memorization occur in non-parametric models as well? So I'll say that it occurs in black box models for sure, and I'll show some results on that. With regard to non-parametric models, I think that it probably won't occur because non-parametric models basically use the label ordering in a very specific way. So you basically force the model to use the labels in a way that looks at similarity. And this, there's kind of no way, in the course of this model, it's probably a lot harder to completely ignore the training data than in the other kinds of models, because your predictions have to, because you literally have to actually use this similarity in order to output the correct label. Otherwise, you have no other way to kind of directly fast track from X test to Y test other than going through the labels in your training set. So I think that this problem, I haven't experimented with it in practice, but I'm pretty sure that this problem won't come up for non-parametric approaches. Okay. Great. So this seems like a bit of a problem potentially. And it's worth mentioning that potentially for image classification, like, we can just shuffle the labels and we'll still be fine. Although it is potentially still perhaps somewhat disturbing that this issue comes up if you don't shuffle the labels. And maybe it's also not a problem if we see the same image classes as training. If we don't see held out image classes, then this model will be fine because it doesn't actually need to use the training data. But it is a problem if we want to be able to adapt with data to new tasks. Okay, so it looks like there's some questions, and I'll take those questions now. So I think I'm going to assume that your hand is up from before. Not sure if I pronounced that right. Do you have a question?
No, actually, I was raising hand for the previous question. That's fine.
Okay.
I was still a little bit confused about why we're able to say that the model ignores the training data set in MetaTrain. Wouldn't it still need to look at the train set in order to correctly classify the new test set images?
Yeah, so basically what happens is, I guess, so I'll get into this a little bit later, but it is possible that it will still learn to pay attention to this data set here. But I guess the important thing to point out is that if piano always has a label of 4, then it doesn't need to figure out, it doesn't need to look at these training examples to tell that that the label should be a 4 for this image. And basically, if there is kind of a consistent assignment of labels to image classes, then it can just kind of memorize that consistent assignment and make predictions based only on the test example and not based on the training set.
Okay, I see. Thank you.
Yeah, I was just trying to reconcile this with homework 1, where we were asked not to shuffle the examples, right? So the input to the LS team for a 2-shot problem would look like 0, 1, 2, 3, 0, 1, 2, 3, or something like that. So is that why we were expecting a lower performance than what we would have when we compared it to state of the art, or?
So to clarify in homework 1, you were still shuffling the assignment of labels to classes, because you would basically randomly sample n classes and randomly assign n labels to those classes. What you weren't shuffling was necessarily the kind of the order in which you pass these examples into the network. So you basically, the labels here would be shuffled and you'd have different assignments for different classes. But once you determine that assignment of labels to classes for that task, then you fix the order of the examples that you pass in.
Okay.
And there's also a few questions in the chat. So asking, but it should always predict 4 for piano and get a high accuracy, right? So it's worth mentioning that when this happens, the model will actually do great in terms of meta training performance. It will be able to very accurately predict that the piano is a 4, that this particular kind of dog is a 2, and so forth. Where performance will drop is when you're given new tasks at meta test time that have new image classes, and the model doesn't know the assignment, doesn't know what label those new image classes correspond to. And then there's also a question in the chat about, do we have a smaller performance gap under 5-way setting compared to a 20-way setting? I can't remember exactly. I think I might be showing results later for the 5-way setting, and we might see that later in the lecture. Do you have a question?
Oh, sorry, I forgot to lower my hand. Yeah, I have a doubt. So we are saying that we have fixed the labels. If we have 10 classes, so we have fixed the labels to 0 to 9. And now if we sample, if we are doing the three-shot training, then we sample 3 classes out of it. So how will the mapping work? Because if we have 3 classes and they are 4, 7, and 9, then how is the cross entropy and things like that gonna work?
So I guess one thing that I'll mention here is that there are still, so in this example, you have 5, you're doing 5-way classification. You have more than 5 classes total in your meta training set, but you're going to be assigning multiple examples to the same label. For example, the label of 4 is both being assigned to piano and also being assigned to carousel. And so basically the classification task now becomes is it a piano and a carousel, or is it some barrels or a singer, or is it this kind of dog or this tank, and so forth. You could also have something where you basically assign, you have n possible labels, n possible meta-training classes, and assign a different label for piano and for carousel, you'll also run into the same problem there, because you'll still, at meta test time, you'll still be giving it kind of new classes, and it won't figure out how to make a prediction for those classes.
And I had another question, the last slide where you showed like it won't be a problem. Can you go to the slide?
This slide?
Next slide, where it is a problem.
Oh, yeah.
Most times, I guess. So I didn't get how the second problem, like know if we see the same image classes as training.
Yeah, so this basically corresponds, like, what it is essentially reverting to is just a supervised image classifier that ignores the training examples and just classifies the test examples. And so if you see the same image classes, the same, like if your piano is one of the meta training classes and you also see pianos at meta test time, then this is fine, because you'll get good accuracy on things like pianos. The issue is if you see new image classes during new image classes than what you saw during training, it won't be able to figure out what the correct label is for that class.
But like here, like MetaLearning does not have like much benefit. It's almost as same as you're doing like normal supervised learning.
Yes, there are some nuances there, like maybe you want to classify, like maybe different tasks correspond to classifying pianos in like different regions of the world or something, and they look different. But that's, yeah, in general, this is a setting that you wouldn't want to apply MetaLearning to anyway.
Okay.
Okay, so let's look at a couple other examples where this might come up and potentially convince you that this is maybe a problem that's a bit more concerning. So we haven't really talked about reinforcement learning yet, but say we have a robot and we want to be able to train across a wide range of tasks and then be able to quickly learn how to do a new task. And here are some of the training tasks. These are actually real training tasks from this benchmark called MetaWorld. And different tasks, like one task corresponds to closing a drawer, one task corresponds to like using a hammer to hit a nail, another task corresponds to stacking an object. And maybe when you tell, for these sets of tasks, you tell it both like this language description of what you want it to do, and you also allow it to collect some data for that task. And you want to be able to kind of quickly be able to quickly learn from a very small amount of data how to do that task. Now, the tricky part is if you give it both the data and this description, it may just memorize a policy for each of that maps from each of these descriptions to the correct actions for that task, and ignores the data and doesn't actually leverage the data in order to quickly adapt. Then when you give it a new task like closing a box, it doesn't know how to interpret close box, and it previously was ignoring the data when it was learning how to solve each of these tasks. So it's stuck. It doesn't know how to do the task, and it also doesn't know how to quickly adapt from data. So this is kind of another potentially more real problem where memorization would really bite in some way. Essentially, if you tell the robot what the task goal is, then the robot can just ignore any trial data that you allow it to use. And then lastly, one more example of this is, say you want to predict the pose of objects, and specifically you want to predict the orientation. So you want to predict the angle at which the object is facing you. And you have data for different kinds of objects. For example, this couch is like at 45 degrees here, 108 degrees here. You kind of do the standard thing of separating out training data sets and test data sets for each task. Now, again, what the model could learn to do here is memorize the canonical orientation for each of your training objects and use that to learn a classifier for each of the test examples and effectively learn to ignore all of the training examples. And then when it's given a new object, it doesn't know what the canonical orientation for that object is, and it hasn't figured out how to use the training examples to infer the canonical orientation. So when you're given a chair, for example, it isn't able to figure out what the orientation of that chair is from a small number of training examples. Okay. Great. So Essentially, the model can memorize the canonical orientation of the training examples. And I'd like to address the question in the chat, which is, can this be considered as some form of overfitting, as the meta-train and meta-test performance will be quite different? And that's kind of exactly right. You can essentially view this as a form of meta-overfitting. And maybe I'll actually skip forward to one slide to describe that, and then we'll get to what we can do about it in a minute. So if we kind of compare meta-learning and supervised learning, we'll refer to this problem as meta-overfitting, where it's essentially memorizing training functions F corresponding to each of the meta-training tasks. And this is somewhat analogous to standard overfitting, except in standard overfitting and supervised learning, you're memorizing the labels for training data points. So you can kind of view it as like a meta-learning analog of standard overfitting, where instead of memorizing the training data points, you're memorizing the training data functions. You're essentially memorizing the functions that solve each of the training tasks, and then when you try to generalize to a new task that requires a new function, you aren't able to figure that out from data, just like how in standard overfitting, you're not able to figure out the labels for new examples if you simply memorized each of the labels in your training set. Okay, so now let's talk about a potential solution to this. So to kind of recap where we're at, if the tasks are mutually exclusive, then a single function cannot solve all of the tasks. This may be due to label shuffling, it may be due to hiding some information from the meta-learner. But if the tasks are non-mutually exclusive, a single function can solve all of the tasks. And when we're in this situation, there's actually multiple solutions to the meta-learning problem. So if we view our meta-learner as something that takes as input a training data set and a test input, then one solution is to essentially memorize information in theta and ignore the training examples. For example, in the pose prediction example, it could memorize the information about the canonical poses of all of the training objects in theta and then ignore the training data set. And then another solution is to carry no information about the canonical pose in your parameters data and instead infer that information from the training examples. And both of these solutions to the meta-training problem will achieve good accuracy on the meta-training set. However, only this example will be able to generalize to new tasks. And it's also worth mentioning that there isn't just two solutions. There actually are essentially an entire spectrum of solutions based on how information flows. So this is kind of one extreme where all the information about the canonical pose comes from the training data set. This is another extreme where all of it comes from theta, but you may have kind of a continuous spectrum of where information is flowing from, whether more of it is flowing from theta or more of it is flowing from the training data set. Okay. Now the cool part about this is this actually suggests a potential solution, which is that if we can control how information flows, we can encourage it to essentially try to put more information, gather more information from the training examples and less information from theta. Okay. So with that in mind, we'll develop a meta-regularization method to try to mitigate this problem. And in particular, one option that we might do is try to maximize the mutual information between the predicted label and the training data set, given your test example. And if we're maximizing this information flow, this will encourage it to acquire information from dtrain rather than from theta. Unfortunately, at least in our experiences, it was a little bit difficult to try to actually quantify and optimize this term. So what we did instead is we tried to minimize both the meta-training loss as well as the information in theta. And this second term will essentially be a regularization term that encourages it to store less information in theta so that it then is encouraged to, as a byproduct, acquire more information from dtrain. And there's actually a pretty nice way to do this. So the meta-training loss just looks like kind of the standard meta-training losses that we've been looking at before. And then there's a way to minimize a bound on the information and theta by essentially placing a distribution on our weights theta. So we're going to have a distribution with mean theta mu and variance theta sigma. And we're going to basically minimize the KL divergence between this distribution on our weights and some prior distribution. And specifically what this corresponds to is basically just adding noise to our weights. So instead of having a kind of deterministic weight vector, we're going to add noise according to the variance here and encourage that noise to not go to zero by enforcing this prior. And then the kind of noisy weights that are sampled from this distribution will be used in our meta-training loss. Now, of course, if you only had the meta-training loss, then you wouldn't, and you only had this term, then it would choose to store no information or a minimal amount of information in your weights. So it is really a regularization term that's trying to encourage it to lead to this solution rather than the solution that ignores the training samples. Okay, so kind of, in essence, this places precedence on using information from the training example over storing information in theta. And if you're interested in learning more about kind of how this is a bound on information in theta, you can look at some work by Alex Alemi as an example. So Alemi et al., I think he has a paper maybe from a few years ago that looks at basically how this is a bound on information in theta, and has some kind of description about how you can optimize this. Okay, and then is asking, is there a common choice for the prior over theta? Maybe standard normal? Yeah, that's right. So typically, the kind of most common choice for P of theta is just a standard normal Gaussian distribution with mean 0 and variance 1. And the reason why this is really easy to optimize is that you can actually write down the KL divergence for two Gaussians in closed form as a function of the mean and the variance, which makes it pretty easy to optimize this. And then I guess there's other things that we'll actually cover next lecture that also make this easier to optimize, that essentially allow you to differentiate through the samples from a Gaussian. But we won't get into that today. Okay, do you have a question?
Yeah, I have a question. Like, from what I understand, like memorization makes like the zero-shot performance on a training data will be quite high if it the network has memorized a lot.
Yeah, exactly. So if it's memorized a lot, then the zero-shot performance will be great for the training classes.
So can we not just like make a loss and maximize this loss, because we know explicitly we don't want zero-shot performance to be high?
Yeah, so that's actually a reasonable idea, and I think that there's a paper that maybe tried to do this, where you basically try to have minimal pre-update performance, zero-shot performance, and great post-update few-shot performance. The tricky part is that it turns out that the model can actually still achieve this while also memorizing. Basically, even if it memorizes the canonical pose information in theta, it may just store it in a way that isn't accessible, or it may just kind of shuffle the last layer of the network or something in some way, such that it looks like it isn't memorizing, but it actually is. I'm not sure if that was the best explanation. But essentially, even if the kind of pre-update performance looks really terrible, that doesn't mean that it isn't memorizing the information in the network. It could just be that it's kind of disguising that information and then exposing it after a gradient update or after you're actually giving it test examples. Okay, just asking, is this KL term more like a Bayesian method where we are learning a distribution over theta? Yep, that's exactly right. So another name for this is Bayes by backprop. I do feel like there's a lot of different names for this. Whoops. And It's actually it's worth mentioning this is actually a common approach for Bayesian regularization on neural networks in general. Although in general, it hasn't been that popular for regularizing neural networks for supervised learning.
Yeah, I wanted to ask, by assuming a prior and using the scale divergence loss to make sure that weights follow this particular distribution, how are we making sure that it's not going to memorize? It can still memorize information, right, even if it follows that same distribution.
So it makes it harder to memorize information, or it discourages it from memorizing information, because you're basically adding noise to the weights and then using the basically weights sampled from this distribution over weights when making predictions. Because you're adding noise, that makes it harder to store information in the weights. And as you make it harder to store information, that is encouraging it to use information from other means if possible, and will implicitly encourage it to use information from the training examples instead. It's worth mentioning that, like, part of the reason why, well, I'll get into how well this works on the next slide, but part of the reason why we might expect this to work is that both of these two solutions achieve a very good meta-training loss. And we're simply just trying to tip the balance towards this latter solution rather than kind of completely changing what it does. And so we really only need a fairly weak regularization term to try to tip the balance towards this solution. And it turns out that things like adding noise to the weights to decrease the amount of information in theta is enough to tip that balance towards this latter solution. Okay, and then it's asking, is the theta here the pre-update or the post-update? So theta is either the pre-update weights in MAML, or they are the meta parameters in a Blackbox MetaLearning model. Okay, and then it's also worth mentioning that you can combine this with your favorite MetaLearning algorithm. You can combine it both with Blackbox methods and with optimization-based methods. So I'll just quickly go over the results, and then I'll answer a few more questions. So for non-mutually exclusive omniglot, which is basically omniglot where you have a consistent assignment of labels to classes, again, we see that MAML does quite poorly. There's this other method called task agnostic MetaLearning for few-shot learning that actually does something similar to what was suggested before, where you encourage the pre-update weights of MAML to, I believe they're encouraging it to have high entropy, which would implicitly be low performance. This also doesn't perform well. It's essentially able to disguise the fact that it's memorizing. Whereas if you apply this meta regularization to MAML and specifically apply the meta regularization on the weights, then you see a really dramatic change in the performance because it's essentially tipping the balance towards the solution that's actually using the training examples. And then on the post-prediction task that I mentioned, also we see also kind of a pretty big improvement in terms of mean squared error from 5.39 to 2.26. Also, if you combine the meta-regularization to conditional neural processes, which is a kind of Blackbox MetaLearner, you also see a pretty big improvement in performance. It's also not quite as simple as standard regularization. So if you apply just like weight decay or Bayes by backprop to conditional neural processes, to basically like all of the weights in the model, not just the ones that correspond to the meta parameters, then you don't see as big of an improvement compared to the meta regularization that I just described. Okay, do you have a question?
Sorry, I wanted to ask, does dropout help with reducing like meta overfitting? Because like it's also adding noise to your parameters.
Yeah, so dropout is actually adding noise to the activations, not to the parameters themselves. If you actually look at this paper, MetaLearning Without Memorization, there are experiments where you add noise to the activations in the form of an information bottleneck rather than adding noise to the weights. And that performs well in some cases, but not in all cases. And there's an explanation in the paper for why we might expect adding noise on the weights to work better.
Mm-hmm. Okay, yeah, thanks. Yes, so when you say that this data contains information, is it possible for us to predict some of the task results based on this theta value? Can we train a network to do the task?
So you're asking, can you predict the performance from the weights of the network or something else?
Yes, from the weights, because you mentioned that this data might contain some information. So barely from this data, we might be able to memorize something, and we might be able to perform the task from this data value.
Let's see. So you're saying that you want to predict basically from the mean of the parameters or the variance?
No, not for this KL divergence term. So so this is a kind of problem of meta overfitting. So you mentioned that this data may store some information. And I'm just
I see what you're asking. Yeah, so you could basically try to understand if the information about the canonical poses and theta, maybe by like training a model to predict the canonical poses from theta or something like that. That's a good question. So I think that in the general case, you may not necessarily know what the kind of thing that it will memorize is, like the canonical pose. Although in some cases you might. I think you could potentially try to train a model to predict canonical pose, and then you could like use an adversarial objective to encourage it not to be able to contain that specific amount of information. Yeah, that could be a reasonable approach, and you could potentially also do this on the activations rather than the weights, or both. We haven't experimented with that explicitly, but it seems like a pretty reasonable approach for reasonable thing to investigate.
Yeah, thank you.
Yeah, so I was thinking about data augmentation, that during meta training, if you were to add random noise or adversarial noise to the task distribution, I mean, would that help solve this problem? Because now we are forcing it to look at the data and not memorize.
Yeah, so there is actually a very recent paper that I think came out on Archive. I think it's going to be at NeurIPS this year, on trying to use data augmentation to mitigate this memorization problem. And so I'd refer you to that paper if you're kind of interested in looking into that. But kind of the short story is that they were able to get pretty promising results by using different forms of data augmentation to solve the problem.
Okay, thanks.
Okay, and then there are a couple questions in the chat that I want to try to get to. So I was asking, can you elaborate on what theta mean and theta variance is? Are they the mean and variance of all dimensions of theta? Yep, so that's correct. So they're basically the mean and variance of the meta parameters. They are quite high dimensional if theta is high dimensional. In principle, you could potentially apply them to only a subset of the meta parameters. And I think that actually in the mammal results that I showed, we found it most effective to apply them predominantly to the encoder of the network, to encourage the later layers to still adapt with data. Yeah, but you can think of them essentially as having the dimensionality of the parameters and being a fixed vector, one for the mean and one fixed vector for the variance. Asking, is there a concept of dropout for the thetas in MetaLearning? It sounds like applying Gaussian noise would be equivalent to that. I think dropout would be probably a little bit trickier to implement because, well, it may be a little bit trickier because when you drop out a weight value to 0, it may be difficult for the network to compensate for that. but I'm not sure. I haven't thought about that too much. When you have noise, though, it's a little bit easier to differentiate through. And then asking, does applying meta-regularization to shuffled omniglot improve performance compared to the non-regularized omniglot? So if you're in the kind of standard omniglot setting and you apply this, I think that it leads to roughly similar performance, maybe slightly better performance empirically. Okay, for the sake of time, I'm going to keep on going because I think that we should try to get to the second part. I don't think I have time to go over this slide, but just one quick thing worth mentioning is that you can actually theoretically analyze this approach and kind of actually derive a generalization bound on the performance that basically looks something like the error on the meta-training set plus the meta-regularization term. And so this allows you to actually recover the meta-regularized objective from this pacmaze bound is what it's called. If you're interested in that, I'll let you look at the slides or look at the paper offline. And then to summarize the memorization problem, we already talked about how it is essentially analogous. It's kind of a meta-learning analog of standard overfitting, whereas instead of memorizing the training data points, you're memorizing the training functions for each of the tasks. And the solution to it, or at least one solution to it, there are potentially other solutions that could maybe be even more effective, is to control information flow. And this is in contrast to standard regularization in supervised learning, where you try to regularize the hypothesis class. Meta-regularization can also be viewed as trying to regularize the description length of the metaparameters, which is somewhat analogous to regularizing the hypothesis class. Although it's worth noting in practice that things like Bayesian regularization and placing a distribution over the parameters hasn't been nearly as successful in supervised learning as the results that I showed previously when you have the memorization problem in MetaLearning. Okay, so now let's talk a bit about MetaLearning when you don't have tasks provided. So we talked a bit about how tasks can come from different sources, depending on the application domain that you're in. But in a lot of application areas, we may not even have data from other tasks or data from other domains that may allow us to help solve the problem. So what I want to talk about for the rest of the lecture is, what if we only have unlabeled data? Can essentially the algorithm propose tasks itself from unlabeled data that allows it to adapt to new tasks at meta test time? In particular, our goal will be to do few-shot meta-learning from unlabeled images or unlabeled text, so that we can then actually be able to solve few-shot image classification problems or few-shot text classification problems that are defined by a human at meta test time. So kind of the problem setup will be during meta training, we'll just have basically like a bunch of like unlabeled data. And then at meta test time, we will have a training data set that's labeled, and also some test inputs that we want to make predictions for. So meta test time will look identical to what we had before. What's different is that during meta training time, we just have unlabeled data, and we need to be able to construct tasks from that unlabeled data that will prepare us for what happens at meta test time. Okay, so first, kind of a general recipe for what this class of approaches have typically done is, first, given some unlabeled data, you want to propose tasks from that unlabeled data. And once you propose tasks from that, you can then run meta-learning on those tasks. So pretty simple, right? Obviously, the hard part is the task proposing part. And that's what we'll talk about primarily on the next slides. And so really the goal of unsupervised meta-learning methods are to automatically construct tasks from the unlabeled data. Okay, so I have another question for all of you, which is if you were to propose tasks from unlabeled data, what do you want that distribution over tasks to look like? Do you have any thoughts on how you might try to propose tasks in a way that prepares you for the tasks that you might see at meta test time?
Have a Gaussian distribution.
A Gaussian distribution. So what do you mean by a Gaussian distribution?
And evenly distributed with a mean at which, so let's say we have a mean at which we have a task and then there's some variance and tasks at each variance.
Yeah, so an evenly distribution, like that seems like a reasonable suggestion. I'm not sure how to specify a Gaussian distribution over tasks. If the task is, well, yeah, that seems very reasonable. Do you have thoughts on like what the mean and variance of that Gaussian distribution would be?
No.
Okay, cool. That's a good start. Do you have thoughts?
Yeah, it seems like proposing tasks is almost like similar to coming up with labels for the unlabeled data set in such a way that you want to get the labels that help you learn the test meta set as good as possible. So you kind of want to come up with labels that are most similar to your test task, if that makes sense.
Yeah, so if you had a way to come up with labels for all of your training data set, then one thing you could do is construct kind of tasks that are from that kind of labeled data set, similar to how we typically do. And you would want those labels to be reflective of the kinds of labels that we might see at test time. So that's a good thought.
Yeah, so for a classification problem, for example, we could look at the data distribution in a different space, like latent space or something, and we could cluster different distribution and each could correspond to a different class, something like that.
Yeah, so we could basically try to have different kinds of tasks potentially. Is that what you're suggesting?
Yeah.
Cool. Other thoughts from?
So we might want to find like a diverse set of tasks that sort of like cover the whole like data set. So it's sort of like partition it, but have each like sort of like task be as diverse as possible. But each task internally contains like examples of that are very similar to each other.
Yeah, so this is also similar, I think, to what maybe I was suggesting, is that it seems like we probably want to use all of our data set and somewhat evenly use our data set rather than kind of focusing on different parts of the data set or skewing our distribution in some way. There are also some suggestions in the chat, such as using self-supervision signals to propose tasks and to maybe partition the unlabeled data into clean clusters, maybe where different clusters are different tasks. So thinking about this problem, the two things that I came up with for the slides is diversity in tasks. And I think this is kind of what you all meant by trying to have more evenly distributed tasks. Essentially, if you have more evenly distributed tasks or more diverse tasks, you're more likely to cover the test task. So the test task is more likely to be in that set of tasks if you have a diverse set of tasks. Now at this extreme though, if you have too diverse of a set of tasks, then you may not be able to actually, your meta learner may not actually be able to pick up on any structure in that set of tasks. And so you also need your tasks to be structured so that few-shot meta learning is even possible. For example, at the extreme where you just sample completely random tasks from your data, there won't be any structure to pick up on in order to learn efficiently with a small number of examples. And so we're going to try to aim for both diverse tasks and structured tasks. Okay, so we'll talk first about how you might construct tasks from unlabeled image data, and then we'll talk about constructing tasks from text data. So first, let's talk about labeling from unlabeled, or meta learning from unlabeled images. And the approach here is actually going to be quite similar to the approach suggested in the chat, which is to partition unlabeled data into clean clusters. And in particular, what we're going to do is we're first going to run an unsupervised learning algorithm to get some embedding space. This is because working in the original image space is quite challenging. So this will allow us to embed images in our training example, in our meta training set to a lower dimensional embedding space shown here, visualized in 2D for ease of visualization. And then what we'll do is we'll run clustering in this latent space, just using k-means clustering. And we'll propose tasks as classification tasks of classifying between images in different clusters. And so concretely what this can look like is we'll cluster actually multiple times. So one run of k-means clustering may give us something like this. Another run may give us something like this. And then to construct a task, we'll sample two clusters, maybe the red cluster and the blue cluster. And the task will be to classify images from one cluster versus images in another cluster. So we'll construct our training data set as these two examples right here. And we'll construct our test example as these two images right here. So this will give us a kind of a two-way, one-shot classification task. And we can then construct another task, for example, maybe by looking at this purple cluster versus this green cluster. And we can also construct n-way classification tasks by sampling n disjoint clusters. And then, of course, once we have these tasks of discriminating between different clusters, we can then run our favorite meta-learning algorithm. Okay, and then the result of this is kind of a representation that's suitable for really quickly learning downstream tasks, because you're training it to be able to distinguish between different clusters given a small data set. Okay, so this is kind of the first approach. How do you get the embedding space? For this, you can use kind of existing unsupervised representation learning methods out of the box, like ByGAN or deep cluster. There are also more recent approaches than this as well. Then we run k-means clustering and propose cluster discrimination tasks. We refer to this method as clustering to automatically construct tasks for unsupervised meta-learning, or cactus. And then we run meta-learning on top of those tasks. So if you're interested in what a mammal on top of a cactus looks like, you get something like this. And if you look at mini-ImageNet, if you run mammal with kind of full labels on the meta training set, you get 62% accuracy. If you compare to different approaches of learning on top of the initial representation space, you get lower accuracy, but you still do somewhat reasonably. If you run mammal on top of the clustered tasks, you get 5-shot accuracy around 51%. And if you use actually the deep cluster latent space instead, you get almost 54% accuracy on 5-way, 5-shot mini-ImageNet. And this is without any labels in the meta training set, just using the unlabeled images in the mini-ImageNet meta training set. So this is pretty cool. We can actually start to approach the performance of a fully supervised meta-learning algorithm. And you really see kind of the same trend of results for 4 different embedding methods for data sets other than mini-ImageNet, like Omniglot, CelebA, and MNIST, also for prototypical networks, and for test tasks that have larger data sets that are larger than 5-shot, for example. Okay, so that's kind of the first approach that we can take. Now, another thing worth considering is maybe in some domains we have some knowledge about what might make a good task. So for example, in the realm of image classification, we know that if we do certain things to the image, the label won't change. So if you drop out some of the pixels, or you translate the image a little bit, or if you reflect the image from left to right, then typically the label of that image won't change. For example, if you take this Omniglot digit and translate it a little bit and drop out some of the pixels, it still has the same identity. Likewise, if you take an image from mini-ImageNet and you reflect it left-right, then this image still has the same class as the image before. And so we can use this domain knowledge to develop a way to propose tasks by simply using augmented versions of our examples as additional examples from that class. So in particular, what this looks like is for each task that we want to construct, we randomly sample n images and assign them labels 1 to n. So for example, maybe we sample these 3 images and assign them corresponding labels. And then for each of these data points, we augment the image using our domain knowledge and assign them the same corresponding labels. And this top row can correspond to the training data set for that example, and the bottom row can correspond to the test set. So we're basically kind of using our domain knowledge about how examples, about intra-class variation within a class, and using that to construct new examples about how the model should be able to generalize after training on these examples. Okay, so this is another way to construct tasks. And again, you can also, once you construct tasks using your unlabeled data set, you can then apply this with a meta-learning algorithm. It's worth mentioning that every once in a while you will sample images that have the same underlying class. And in practice, that's often okay. It will give you kind of more diverse tasks, and some of the tasks that you're giving your meta-learner won't reflect the kinds of tasks you see at meta-test time. What's most important is that the meta-test task is kind of within the convex hull of the tasks that you're training on. Asking, is this similar to self-supervised learning? Yes, so this sort of data augmentation has also been pretty successful in the realm of self-supervised learning as well. And so if you take this approach, and for OmniGlot, use translation and pixel dropout for augmentation, and for Mini ImageNet, you use a mixture of translation, rotation, and shear based on this kind of auto-augment approach in the paper by Kubik et al. We see results that look like this. To summarize, there's really outstanding OmniGlot performance. The performance actually almost approaches the fully supervised performance. So in the 5-way 5-shot setting, it's like 95% versus 98%. On the 20-way 5-shot setting, it's 92 versus 96. This is because in OmniGlot, we have pretty good domain knowledge about the images in OmniGlot. And then in Mini ImageNet, the performance is kind of slightly below that of Cactus. This is probably because we don't have quite as good domain knowledge about all of the kinds of variation that natural images have within a class. And it's hard to construct forms of augmentation that cover all of that intra-class variation. Okay. Do you have a question?
Yeah. Do you think you could go back to the first slide with the title, Can we meta-learn with only unlabeled images?
Yeah.
So I'm not sure if I'm interpreting this the wrong way, but it seems like this is just kind of teaching, or it's learning how to classify images that are like visually similar based on like the tasks that are created. So how are we supposed to get an image classification, like of say like classifying a fruit as a fruit versus like a jellyfish as a jellyfish out of this?
Yeah, so I guess it's worth mentioning that the goal of this kind of approach isn't to get a classifier out of it. The goal is to be able to do few-shot classification at test time. And so these tasks don't have to be perfect, and they don't have to like perfectly match all the tasks you're going to be seeing at meta test time. You simply want to cover a pretty diverse range of tasks that you might potentially see at meta test time. And if it kind of learns to generally kind of distinguish things, distinguish kind of a diverse range of things, then maybe from a small amount of examples of those things, then at test time it may be able to also distinguish things in the meta test tasks based on a small number of examples for your meta test task.
So at test time, sorry, go ahead.
Oh, go ahead.
So at test time, would we be giving examples that are all like within the same class that like say we would want to classify, or would it also be like a wide variety of things?
Yeah, so at test time, maybe you want to kind of be able to classify between your two pets or something. And so you would give it like 5 images of one pet, 5 images of another pet, and then adapt the model that was meta-trained on these examples to your classification problem.
Got it. Thanks.
It's also worth mentioning that this approach is probably by no means perfect, and there's probably a lot that we could do to improve upon this. It's also very challenging to kind of, in a completely unsupervised way, distinguish different classes. I think that the power of this, though, is that these tasks don't necessarily need to exactly correspond to true semantically meaningful tasks, as long as you have essentially a means to cover a broad range of structured tasks. Yeah, so these proposed tasks are designed to help to train the image encoder, which will be used at test time. So these tasks will be used to train kind of a MetaLearning algorithm, such as a set of initial parameters with MAML. And then at test time, you want to run gradient descent or run your kind of, or run prototypical networks or something on a small data set and be able to transfer to that new task.
Yeah, so I was just wondering, so if I understand it correctly, the cactus approach, which was the clustering, is like an alternative to the one where you are incorporating domain knowledge, right? Like there are two different approaches. Whereas
Yeah, these are basically two different approaches.
Yeah, right. So in cactus, you just don't incorporate any domain knowledge, and you just do unsupervised clustering for defined tasks. But in this, I guess, UMTRA, you call it, you just like augment existing data like images and use that as your test plot. If that's the case, then in this UMTRA case, what happens if you, let's say, sampled like 3 or 4 like same breed dog images in your N? Wouldn't they be then considered as like distinct classes?
Yeah, so that's kind of one of the failure modes of this kind of UMTRA approach. Is that with some probability you will be sampling images from the same class. Luckily, if you have a large number of classes in your meta training set, that will happen with relatively low probability. And again, even if some of your tasks aren't representative of the kinds of things that you see at meta test time, that's kind of okay, as long as the predominant part of your meta training tasks that are proposed by the algorithm do cover the meta test tasks. But this is kind of a downside of this approach.
Cool, thanks.
Okay, and now let's briefly talk about MetaLearning with only unlabeled text. So the first option here is to formulate it as a language modeling problem. This is an example, this is what we saw when we looked at GPT-3, for example, where dtrain is a sequence of characters, dtest is the following sequence of characters, and we saw with that how basically you can use a lot of unlabeled text data to train a model such that it can learn things like simple math problems, spelling correction, and translating between languages. So this is one successful approach for using only unlabeled data. When might we not want to use this option? So I think that this sort of option is a bit harder to combine with optimization-based MetaLearning because you'd have to somehow adapt your model with gradient descent on the unlabeled text that you're given. And I also think that it may be harder to apply to classification tasks because the model is just outputting kind of text rather than classification labels, such as labels for sentiment classification or political bias. And so I think that you could apply it to classification tasks with a bit of work, but it's probably a bit harder to do because you have to process the natural language output that it produces. Okay, so another option that was actually recently proposed by Bansal et al., it actually I think came up on arXiv within the past month or two, is to construct tasks by masking out words. So different tasks will basically correspond to classifying the word that was masked out and trying to figure out what that word was. Specifically, what this looks like is for each task, you can sample a subset of n unique words, assign each of those unique words a different label ID. So for example, maybe you sample 2 words, democratic and capital. You assign them the ID of 1 and 2, or the label of 1 and 2. And then you sample sentences with each of those words, masking out that word, and construct the training set and the test set with the masked sentences and the corresponding word IDs as the label. So as a concrete example, your support set might look like this, where this is kind of democratic and capital again, and the word that was selected is masked out, and the model needs to predict which word was masked out. So this has kind of both inputs and labels, and then the test data set corresponds to a new sentence with that word masked out and the corresponding label. This is a pretty simple way to construct a large number of classification tasks from text. And it works pretty well. So they had actually a lot of results. Everything to the left of this bar is kind of using an entirely unsupervised pre-training approach. And then everything on the right also incorporates some supervised tasks. If we first look at the entirely unsupervised pre-training results, BERT is like a standard self-supervised approach where it's actually quite similar to the masked, to the method proposed here. Whereas SMLMT is the proposed unsupervised meta-learning algorithm that we just went over. And so we see that in general, these approaches tend to perform pretty similarly, except for perhaps on the disaster data set where the unsupervised meta-learning approach does a lot better. And then in this more supervised setting, they compared to multitask learning approaches where you train on a number of supervised learning tasks and then fine-tune on a new task. They also compared to Unlabeled, which is an optimization-based meta-learner based on MAML, where this is trained also only on the supervised tasks. And then they compared to their hybrid method, which does unsupervised meta-learning on their proposed tasks, but also integrates the supervised learning tasks into the meta-learner. And overall, they find that this meta-learning approach that kind of incorporates both unsupervised meta-learning tasks and supervised meta-learning tasks is able to do significantly better than these other approaches that don't leverage the unsupervised tasks or don't leverage the supervised tasks. Okay, so we're running out of time, so we'll skip this last part. And then, yeah, to recap, we talked about memorization. We talked about different ways to propose tasks from unlabeled data. This gives us a class of unsupervised meta-learning algorithms. And yeah, covered the goals of trying to talk about how and when memorization will occur, and also techniques for constructing tasks.
I have a question regarding this language classification task as few shot. Determining the class using like sampling different words and masking them. So do you think it would matter like if the classification task can be made harder, like in the sense instead of sampling words like democratic and capital, let's say if we sample words like democratic and republic, and because those 2 words can fill the context, but the model need to know some other knowledge as well to find out whether the democratic word would be the best choice or the republic word.
Yeah, that's a great idea. I think that if you completely randomly sample words, then you'll probably get words that are very easy to distinguish between. Like if you sampled, for example, between like democratic and like with or rival or something, or even like words that are like nouns versus adjectives, as in this example too. So yeah, I think that some sort of way to encourage the method to find harder pairs of words and harder sets of words would probably actually lead to better performance from these methods.
Okay.
Yeah, and actually, one more note on that is you may also want to make it not too hard. So if, for example, the 2 words that you pick are like purple and blue, and there are many situations where you can't necessarily distinguish when, like maybe like she has a purple water bottle or a blue water bottle, you can't really know which one is the right color, then you're going to be giving it tasks that are impossible, and that may lead to overfitting and worse performance. So there's a bit of a balance to strike there.
So yeah, so just to follow up on that, so would you consider this to be a like a possible project exploration idea for this class?
Yeah, I think that would be a great direction for a project.
Okay, thank you.
Hi, I had a quick question about the loss plus beta information flow, the slide that you had that on.
Yeah.
I'm curious, the beta itself, if you tried decaying it and not keeping it constant, what would happen?
Yeah, so beta is a hyperparameter here that is actually pretty important because you need to make sure that it's like strong enough, but also not zero. It could make sense to decay it if it's having trouble finding a good solution to this problem. So for example, you may want to start it as being high and then decay it to be lower. And if you start it as high, basically, it will encourage it to really use anything that it can in detrain. And then if you kind of decrease it over time, then it can store more information in data. So that seems like it could be a reasonable approach, especially if finding like a single value of beta is hard.
Okay, thank you.
I had a question about, I think, your final slide with all the results. And because in that slide, it shows like only for the disaster task, the unsupervised learning works better. So is there any like specific characteristics? And is there like any reasoning why just for that specific task, unsupervised works better than supervised? Because the intuition, I think, is that supervised is always better because you just use more information, right? Or is that not true?
Yeah, so first it's worth mentioning that you also see an improvement on the political bias task when you have a larger number of shots. And also, I actually cut off this table. There's actually more data sets that they tested on too. I just couldn't fit it on the slide. And I think that there were also some more where the unsupervised method was doing better. I don't quite understand why the fully unsupervised method is doing better in this case than the one that incorporates supervised tasks. My intuition would be that like incorporating supervised tasks should always help. It's possible that they have an explanation in the paper. I didn't see it when I went over the paper, but I may have missed it.
Right. Okay. Yeah, I'll take a look at the paper then. Thanks.
I guess one thing that I could mention is that maybe, I can't remember exactly what supervised tasks that they were using to incorporate into meta training, but maybe those tasks were quite different from the kinds of tasks that you see in this test task. And maybe the unsupervised tasks are just a little bit closer to the kinds of tasks that you see at test time.
Right. But then it might also be harder to get the right unsupervised task, right?
Yeah.
Yeah, okay.
Hi, I have a question on the slide 16. So where you have all the sofa and objects and angles. Yeah. So for this type of task, the labels is the angle of the object, right? And for the model to infer from what's the angle is the test set, it needs to know the relationship between labels instead of like regular classification task. Each label is independent. So how does the model learns that from this?
Yeah, so you need kind of more than, well, I guess it does need to kind of understand like if you need to kind of look at two images, either like two of the images in your training sample or one image here and one image here to be able to kind of compare the orientations. The methods like prototypical networks like already build this in to some degree because you're kind of comparing them. Although it's also a regression task, so it'd be a bit tricky to apply things like prototypical networks to it. In general, though, like models like Blackbox models and MAML do incorporate information from multiple examples. MAML does it by averaging the gradient, and then Blackbox models do it by processing all of the examples as input. And so they have the capacity to look at kind of multiple examples jointly to some degree. And that's kind of one way that allows them to solve this task. Does that answer your question?
Wait, so you're saying this is a regression task instead of like 360-way classification?
We treated it as a regression task. You could also treat it as a 360-way classification task.
Okay. So do you also apply, another question would be, do you also apply a uniform or a global angle measurement across different images, because you can define the angle. So it depends on how do you aim your axis, right?
Yeah, so that's kind of what I meant by the canonical orientation. That's kind of like the base axes. However, it's with different object shapes, it's hard to determine, like basically each object has to have its own canonical orientation. It's difficult to align objects in a way that allows you to have the same canonical orientation for all the objects.
Okay, cool. Got it. Thank you.
I have a question regarding like this cactus method. So like in the cactus method and the UMTR, is there like a work combining the two schools? Because like UMTR has a failure method where you can sample multiple classes, but if you like use the cactus method to like first cluster them and then always select from different clusters, so that will maintain that. And that is second way when you put like the test set is constructed from the training set, so you won't be much biased by the issues that the clustering method might have.
Yeah, so I don't know of any methods that combine them. One kind of naive way to combine them would just be to train on both sets of tasks. But there may be more interesting, sophisticated ways to try to combine them as well.
And then one question I have regarding the last slide in the text classification. So like if you go to the results table.
Yep.
Then it's like the gains between BERT and all the other meta-learning method is like it's very less, like maybe like a 2%. So how do you like, is it like practical to do this given like if you're like fine-tuning on BERT, it's much cheaper than like training the whole meta-learning method for like 2% of gain?
So BERT is a really strong baseline here, and it does perform pretty well. Although I will say that kind of, even though the performance is like, you see only a small improvement in some cases, like from 49% to 52%, there are other settings where you see a much larger improvement. For example, from like 42 to 56, that's kind of a 14% absolute improvement, or like 38 to 63. Or yeah, there are kind of other examples as well. So like 54 to 61. There are examples where you see a pretty big improvement. 50 to 70 is another. But yeah, BERT is a pretty strong baseline, and has also been kind of heavily